Hello and welcome back to my YouTube channel. Let's see about interpolation. What is the golden circle of curve fitting? Start with three basic questions: why, what, and how, in the same order. So why do we use curve fitting? We want to approximate data with continuous functions. So the next question is, what methods are available for curve fitting? Popular methods are linear regression, polynomial fittings, etc. And finally, how to do curve fitting? We can do it by interpolation and projection. In this video, we will focus mostly on interpolation. So let's see the why question in detail. So why curve fitting? First one is to make sense of the raw data. So we have a scatter of points and we want to make sense of it. So let's say we have price versus year. So we fit a straight line to see how the trend is going. Second one is to get empirical relationships. We want to have functional representation of the point data. So here we have a more complicated point data. And since we know it is of the form a minus e to the power b x to the power c. So we want to play with a, b and see the different values. So we see this one fits the data very well. But if we have to have simpler representations, we don't want exponentials, we want polynomials. So we can have that same function and approximate it using the polynomials. The polynomials of order 2 looks like this. Then we have a polynomial of order 4 that looks like this. Then we have a polynomial of order 8 which is very similar to the exact data. Now since the y is clear, we'll just conclude with it and have this information that simplest approximation can be done using polynomials. To assert on this point a bit more, we'll see a Taylor series expansion of ln x about x equals to 1. So here you'll see that ln x can be written as minus 1 to the power n plus 1 times x minus 1 to the power by n. So this is the exact function. Now we want to approximate it using polynomials. If we approximate it by one term, it becomes x minus 1. If we use two terms, then it becomes x minus 1 minus x minus 1 square by 2. Similarly, if we go on increasing the orders, you'll see that the fitting improves. This is for the cubic. And then this is for the fourth order. The fourth order is very similar to ln x. So again we get a hint that polynomials can approximate continuous functions to any desired accuracy if we keep increasing the number of terms. So now let's look at a formal definition of Taylor series. It's a polynomial approximation using the derivatives of a point at x equals to a of the function. If we replace a by 0, then it becomes a Maclaurin series. Now Weierstrass came up with this approximation theorem that any continuous function f of x on a closed interval can be uniformly approximated by a polynomial function. If we have a finite number of approximations, then it is not exact but very close to it. Now the question comes, how do we measure this difference in the exact and the fitting functions? So we define a norm. We derive it from the Euclidean norm of 2D and 3D geometries. So if we have 2 points, the distance between them is given as this. Now moving to vectors, we extend this definition by measuring the abscissa and the ordinate of the vector. So we have this 3 and 2 as the abscissa and ordinate. Then we use the Pythagorean theorem to measure the length of a vector. Now we extend this definition further to a difference of vectors. We know that difference of two vectors is again a vector. So we first calculate the difference vector and then calculate the length of that vector. Moving to difference of two functions. So now if we have two different functions over a domain, then we take the difference of the two functions, square the difference, and then integrate that particular function over the domain and square root after that. This is the definition of a norm. Now let's quickly see by an example the two types of curve fitting. First one is the interpolation and second one is projection. In interpolation, the fitting function satisfies the exact function values at certain number of points, while in projection, we want to minimize the global Euclidean norm. There is one more name to this Euclidean norm. Please comment down below the exact name of that Euclidean norm. So now the interpolation and the projection fits looks like this. So interpolation satisfies the function value at 3 points while projection doesn't, but the norm will be lower in projection. To do interpolation kind of fits, I have written a code in MATLAB published on GitHub. You can go and access it. So this is a description of the algorithm of the code. So we want to do fit using interpolation. So we have this polynomial function p of x, which is c0 plus c1x plus c2x squared, and it goes on till infinity. For let's say order 2, if we want to fit a quadratic fit, then it reduces to c0 plus c1x plus c2x squared. So what we essentially want, we want 3 conditions to find out c0, c1 and c2. To this cause, we find 3 equally spaced points on the domain. We call it x0, x1 and x2. Now, we calculate the exact function at these points. So we get 3 values of y, y0, y1 and y2. Now we construct the famous Vandermonde matrix. This is nothing but the coefficients multiplied by the monomials written in a matrix form. Now finally we invert this matrix and multiply it by y to get our final coefficients. So after doing this for this certain problem, we get p of x equals to 0 plus 7.2744x plus 0x squared. So our f bar x becomes 7.2744x. In the second part of the code, we calculate the errors associated with it. So to do the error analysis, we first calculate the exact function values. Then we calculate the fitting function values. Now we define the difference function error E is equals to f exact minus f bar. Then we plot E square instead of E on the same domain. Then we use a trapezoidal kind of a rule to integrate those error squared functions. Then finally we take square root to find the norm. Now since we have understood the code, let's use it to do a lot of fits. First example is x to the power 4 sin x. And increasing the order, we see that the error is decreasing. By the time we reach the 6th order polynomial, there is almost no difference between the exact function and the fitting function. So we can say for smooth functions, polynomial fittings are really good. So let's take one more example. Now the second example is y equals to e to the power x. Again here, since e to the power x is a very smooth function, so we see that the error decreases very fast. With increasing order of polynomials, the curve fitting gets better and better. By the time we reach p equals to 5, there is absolutely no difference at all between the exact function and the fitting functions. So now you might be wondering then what is the issue with interpolation kind of fits. So let's take one more interesting example to show you my point. Now y is equals to e to the power minus 0.2x squared times cosine of 5x. Now interpolation gets worse. Whenever the points are too close and varying a lot, then interpolation is not good at all. Here you can see, even with an increasing order of polynomials, the curve fitting is not very good. Even with p equals to 9 or 10, we are having a huge error, particularly at the boundaries. For the final example, we take heaviside x. That is, y is equals to 0 for x less than 0 and y is equals to 1 for x greater than 0. Now again we see a sharp increase. It's a step function. At x equals to 0, it has a discontinuity. Again we'll see that the polynomial interpolation is never able to capture this. Even with higher order polynomials, we are still not close enough to the exact function. So Weierstrass theorem said that for continuous functions, polynomials are good. But can we do something good even for discontinuous functions or functions with sharp gradients? So these are the questions for the next video. How can we improve the quality of the fit? Instead of points, if we use the exact solution, will it help? Or can we have uniform convergence? So to find the answers, stay tuned and please download the codes and start experimenting. Get your hands dirty and I'll see you around. Thank you.